Hello again. We're gonna redo 7.8, but I'm just gonna add uh, kind of what I did. The sound was not working properly, so it's gonna be kind of odd everything's written. But I'll explain what we did and we follow on. So it's gonna be a short video. So number 8, we are trying to integrate from 1 to infinity this function. Well, we notice infinity is not our traditional value. Normally we need a number and an interval. So we ignore that completely like we agreed, and we say, alright, you know what, let me look at this. If I am gonna integrate this, this is really 2x plus 1 to the negative 3. And if I add 1 to the power and divide by that, that would be this. So I end up with that integral. And here I will say, well, let me add, I'm going to go from 1. And this is where I add t and I take the limit as t approaches infinity. What I'm trying to do, I'm trying to avoid writing from 1 to t and the limit as t approaches infinity on every step. So I'm accepting that. Or, if you really don't see it yet, now if this is linear, you could just divide by whatever that coefficient is and things will work nicely. Or you could do a u sub if you really like until you get the hang of this. It takes time. So you could let u equal 2x plus 1 and du will be 2x dx. dx is du over 2. So here, now you're looking at this from the green point of view, and from that, this is your u, and your du is right there. So if I plug that in, this will give me the 1/2 du, and this is my u right there. And then I'll write this as u to the negative 3, add 1 to the power, divide by that. Either way, I get the same results. Here I come back and I say, well, I'm going to replace u by what equals, and this is where I introduce the 1 to t and the limit as t approaches infinity. Again, just trying to avoid writing the limit all the time. And then if I integrate this, well, throw the t in, throw the 1 in, I will get this function as t approaches infinity. Well, this approaches 0. How do you know that? L'Hopital, section 6.8 talked about that 1 over infinity is 0. So I'm left with a constant. And if I'm left with any constant, anything that's not infinity or negative infinity, this integral converge. Just like we did back in 6.8. Number 14. If I start on number 14, I'm trying to integrate. Again, we have a problem with this infinity, from 1 to infinity. Well, I use a u sub. I let u equal the exponent. du is right there. So that's my du, and that was my u. And I know the integral of e to the u is e to the u, and I proceed. And now I substitute what u was back in, and now I introduce the limit as t approaches infinity from 1 to t, and that's how it always works. I leave this until I integrate, otherwise I have to drag that limit with me every time. And as t approaches infinity, right, that will approach as 0. That'll be a 1. So I'm getting a number. It doesn't matter what the number is. Therefore, the series converge. So this is one type of indeterminate. Another form of indeterminate is a bit tricky, and let me show you how that works. Suppose that I am looking at an interval from a to b. And they say, suppose the discontinuity happens to be at b. So I'm integrating from 1 to b, and we have an issue with this b. It seems the function is not continuous. Of course, there are examples on that. Well, if this is the problem, do you see that I can only approach b from the left? So when I write the limit, it has to be from the left, and that makes a difference for, say tangent, whether you approach pi over 2 from the right or the left, depending if you're looking at e to the tangent. From the right, it's infinity. From the left, it's negative infinity, and vice versa, or vice versa, I said them backwards. And if I'm looking at the same idea, if I'm looking at, so here I would say, well, I can only approach the limit, I can only approach b from the left. On this interval, suppose we have a to b, and the problem is happening, oh man, forgive me, the problem is happening at a. Well, again, doesn't that indicate that I can only approach a? If this is the interval, can't I only approach a from the right? So when I want to take this out and replace it by t, I can only take the limit as t approaches a from the left. And if I happen to have a discontinuity at a point c, and c happen to be between a and b, so there's a and b. And you know what, highlight is better. C happen to be in that interval somewhere. So let's say this is the line. This is A. This is B. And this is C. Well, guess what I'm going to do? I'm going to split this into two parts. One part is going to deal from A to C, and the other part will deal from C to B. And when the time comes, I can only approach C from the left, and I can only approach C from the right when the time comes. And I'll do an example on that, and we'll see how that goes. So now the video ended at 34, so let's look at this first problem. I'm looking at, so if you glance at that, again, the way you would know that you're supposed to do this, on your test, this would be a separate problem. The test will consist of 7.1 through 7.5. That would be like the first portion of the test. 7.7 by itself, approximate, find this, find that. And at the end, it's going to say literally what the directions say here. And let me show you really quick. The directions were determine whether each integral is convergent or divergent. Evaluate those that converge. That gives you a hint that when you see something like number 28, that you wouldn't just integrate, right? And then add 1 to the power and throw a 5 in and throw a 0 in. You would know that something could be wrong whenever you say whether converge or diverge. This is really all what you have to do. I'm looking from 0 to 5, and I notice this is not continuous at 5. We have a problem. So here, it's really not included. Well, can you see that we can only approach 5 from the left? And for some problems, it doesn't matter as far as the solution, but for others, it does. And it's not whether it matters or not. It's the correct way of writing things. So I integrate. This is 5 minus x to the negative 1/3. Since this is linear, okay, all what I'll do, I would add 1 to the power, divide by that, and divide by a negative 1. So basically, the actual integral is right there. Evaluate from 0 to t, throw the t in, there it is, throw the 0 in, there it is, and we know that, so this is a radical, I could just substitute the value in. I could just take this negative 5 and plug it in. Right, 5, and that will be 5 minus 5, that's 0, therefore I'll get a number, and this will converge. Versus, when I get to this problem, I'm glancing at it, and I notice that we have a discontinuity, we have a problem when w equal to, and I notice that the interval is from 0 to 5. So there's no problem at 0 or 5. The problem happens at 2. So what I do, I split this up. I'll say, all right, let me integrate this from 0 to 2. Oh, you know what, this is too thick. Let me use the other one. Or actually, let me shrink it down. So this portion right here is that right there. And this portion right here, come on, do that for everyone, is that piece right there. And there it is. And now it's simply two integrals, nothing more. Well, how do you integrate? How would I integrate? I have a couple of options. I would take that and say, all right, well, either I use long division, w divided by w minus 4. This is section 7.4, right? This is an improper fraction. And w divided by w is a 1. You multiply, subtract. So this turns out to be, oh, look at that, I forgot to write the w. Or there's a nice trick that students do. You could say, I'm going to subtract 1 and add 1. So basically, they look at the denominator and they say, well, if I subtract 1 and add 1, that right there is a ratio of 1. And there it is. Whatever works. Bottom line, I need to get this far. And I know this is w plus twice natural log of absolute value of w minus 2, evaluated from 0 to t. But do you notice on this first portion, I can only approach 2 from the left. Now, we get to what this means. Let me elaborate on what this means. So, we have, and this is for you, some of you that always forget to put the absolute value on a log and tell me it's the same thing and all of that, which, you know, I say the same thing as well. I'm just kidding. So, we're looking at this. Y equal natural log of w minus 2. Well, without the absolute value. Of w minus 2. We'll shift the graph 2 units to the right. The asymptote will be at 2. And the graph will look like this. And if you remember that homework problem that we didn't like and you complained about, when you put an absolute value around the argument, that reflects the graph normally with respect to the y-axis, but in this case it's shifted 2 units to the right. So that's what the graph looks like. So now when I say, hey, what is the limit as t approaches 2 from the left? Well, isn't that negative infinity? And if one of those two, keep in mind, we have two portions. I know I cluttered those with all of these arrows. We have two portions. We have this and we have this. If one of them approach infinity, if one of them, the whole series diverges. You don't have to worry about the second piece. And if the first was to converge, then I would have had to do the second piece, which I didn't have to do in this case. And that's the part that we missed. Okay, so the notes are already there. I'm going to upload this. And you could just hear it over. And I think, yeah, the rest is in the last section. Alright?